Okay, what do we already know about heat? We know that the amount of heat equals mc delta T. That number can be positive or negative. You know, if you're gaining heat, it'll be positive. If you're losing heat, it'll be negative. So we already know that. I don't remember if I mentioned already, but for some weird reason that I don't know, we use the letter Q to represent heat. Don't know when that decision was made, but so that's what we already know about heat. And now something new. What I want to do is I want to think about a beaker or some kind of a vessel, and inside that vessel we've got some ice. Okay, so this ice isn't just at 0 degrees. Wherever it is, it's colder than 0 degrees. We're going to say that it's at negative 10 degrees Celsius. And in our minds, we're going to imagine a heat source heating that ice up. Okay, so what's going to happen? Well, what's going to happen is, you know, the ice is going to melt, but I want to keep track of this on a graph. So I'm going to sketch a graph over here, and on the bottom I'm going to have time. I'm going to keep this candle going over a period of time, or this heat source, and I'm going to keep track of temperature over here, and I'm going to use degrees Celsius. So my graph needs to start at negative 10 or so, so I need to have negative 10 on it, and I need to have 0 on it, and I know it's not to scale, but I also need to have 100 on it. Okay, so I'm going to heat this hunk of ice up. I'm going to boil it, and I'm even going to catch the water vapor, and I'm going to heat that up. So the first part of this graph looks exactly like you would expect. We're starting at negative 10 degrees at time 0, and we're adding heat to it. So as we leave the heat on, the graph is going to go like this. Now you know that once the ice gets to 0, that's you know, ice's or water's melting point. So you know that once you get there, then this thing is going to start to melt, and then we're going to have some water in here. We're going to have an ice and water mixture. Now the part that might surprise you, if you don't remember this from 9th or 10th grade, or even 11th grade, I guess, but what might surprise you is that when we have this ice and water mixture, the time temperature graph looks like this. It stays flat. Okay, so that's kind of weird. That's something that is new to us. At least I think it might be new to us. So what's unusual is that, you know, we're still adding heat, but that heat isn't raising the temperature. The temperature's staying the same. And we have a name for that. When you add heat and the temperature doesn't stay the same, we call that latent heat. And latent is an old word for hidden. I don't remember for sure, but I suspect it's a Latin root word there. So latent heat is called hidden heat. So after a time, what's going to happen is our ice is all going to be gone. And once our ice is all gone, then the graph does what you'd expect. The graph again starts to go upward. Okay? So our graph, as time passes, our graph continues to go upward, and then the same sort of thing happens once we hit 100. Once we hit 100 degrees, what we notice in our container here is we notice these tiny little bubbles rising up, getting bigger and popping, and what's happening is all these little water particles, they're becoming water vapor, and they're just jumping out mostly into the room. Okay? And if we watch the temperature while this boiling is happening, what we notice is that the temperature stays at 100 degrees. So this is another example of that hidden heat. We're still adding energy, but strangely and weirdly, the temperature isn't changing. Okay? Now, if we imagine that we were somehow capturing all these gas particles and kept on heating them, then the graph starts to do exactly what you would expect again. The graph starts to go up again like this. Okay? So that's this graph. This is what we call water's heating curve. And, you know, different materials have different looking heating curves, and this is my ugly drawing of water's heating curve. Okay, where were we? I just took a break for a second and pretty much forgot where I was. Well, we already know, let's see here, we've got the temperatures changing there, there, and there. So in those three places, we use this equation, and we can figure out how much heat, if you're going to the right, how much heat is going into the substance, or if you're going left, we're figuring out how much heat is coming out. So, excuse me, that's where you use that equation. But it's pretty clear that this equation won't work where the graph is flat, because we don't have any delta T. So we need a new equation, and it's actually very easy. In the flat parts of the graph, that would be this part and this part. The equation is just Q equals mL. Okay, and I'll go into that in just a second. Let me highlight this here. So those turquoisey parts, that's where we use this equation. So where the graph is flat, the temperature's not changing, and this is called the latent heat. We already talked about that. And down here where we're talking about melting and freezing, that is called this constant right here. We call it the heat of fusion. And fusion is just a fancy word for freezing. Think about molecules of water fusing together to make ice. So that's why they call this heat of fusion. And up here where the water is boiling, of course, we make up our fancy name. We call this the heat. The L for this is the heat of vaporization. Okay? So we can actually solve this problem. We can figure out how much energy must have gone into our water, and the only thing I didn't give you that I could have or should have given you would have been the mass. So I'm just going to make up some mass. I'm going to say, let's say the mass of water was 200 grams. That's 0.2 kilograms. And we started the graph at -10, so our temperature original was -10 degrees Celsius. And just for the heck of it, let's say that we're going to go up to a final temperature of 110 degrees Celsius. So this problem is actually a super simple one. You guys are going to think this is a breeze. What we have to do is we just break this problem into 1, 2, 3, 4, 5 little parts. We solve one easy equation for this part, one there, one there, one there, and one there. We take our 5 different answers, we sum them all together, and then we're done. We've got our answer. Okay? So, let's get started. Let's do this part right here first. So for that part of the problem, our temperature original was -10. Our temperature final would be 0. Our mass the whole way through is going to be either 200 grams or 0.2 kilograms. We've been kind of sinking into grams lately, but I like being in kilograms better. And then, since we're using MC delta T, we need to know what C is, and C is and we're not talking about water here. We're talking about ice. So I need to go and find it. Oh, looky right here. Ice -10. So, whoops. So ice at -10 is 2.05, and that's joules per gram. So that comes out to 2050, just slide the decimal 3 places to the right, and joules per kilogram. So all we've got to do is plug these numbers into that equation, and we'll have our first answer. So let me grab my calculator here. So our temperature difference was 10 degrees. Final minus original, 0 minus -10 is 10, times our C, which was 2050, times our mass, which was 0.2, and we get 4,100. So that means this chunk of the graph right here, 4,100 joules of energy went into that ice to get it to melt. So then the next part, this flat part right here, we're going to use the easy equation, Q equals mL. And that is going to be our mass, which was 0.2. And then we need to find L. And this was the heat of fusion. So that is the heat of fusion of water is... And it's nice. It's already in joules per kilogram. So 3.33 times 10 to the 5th. Okay, so L equals 3.33 times 10 to the fifth. Okay, so all we've got to do is multiply that number times 0.2. So we've got 0.2 times 3.33 times 10 to the fifth, and we get 66,600. Okay, so this chunk of the graph is 66,600 joules. And then this part of the graph right here, this this part that's going upward, why is my eraser not working? I have no idea. And this is just going to be the MC delta T thing again. So I guess I could just recycle this chunk over here if my eraser would work. Okay, there we go. So for this chunk of the graph, our original temperature was 0, and we're going up to 100, so our final temperature is 100. Our mass was our 0.2, and the C for water, I need to go back and consult a table. Specific heat for water, and that's 4.186, but that's per gram. I want kilograms, so it's 4186. So 4186. So without actually writing it down for you, I'm gonna go TF minus TO, 100 minus 0, so that's 100, times our mass times 4186. And we get 83,720. Okay. Ooh, that's ugly. And that's joules. Okay, so that takes us to this other flat spot right here, where we're going to use the easy equation again, Q equals ml. So that's just going to be 0.2 times, this time it's going to be the heat of vaporization, because now we're boiling. And so the heat of vaporization of water is, let's see, heat of vaporization for water, 2.26 e to the 6. So 2.26 e6. Okay, so 2.26 times 10 to the 6, that's our L. So for that part of the line, we're going to have our mass, which was 0.2 times 2.26 times 10 to the 6th, 452,000. 452,000. Why is it coloring it that way? I have no idea. And then for the last chunk of line, we go back to our MC delta T equation again. And our mass, as always, was 0.2. Our temperature final was 110. So for this chunk of graph, our original temperature was 100. And C, specific heat for water vapor. So we're going to have to consult a table. Let's see here. Ice, water. Uh-oh. Going to have to go Google. Give me a second. And the specific heat for water vapor is 2010. I guess I should say that that's not just the water vapor, it's the steam, the mixture there. So 2010. So all I've got to do then is apply those into that equation, and I've got my final chunk of my answer. So MC delta T, well, the temperature difference, the delta T is just 10. So I'm going to have 10 times 0.2 times 2010. And I get 4,020. Okay, so 4020. So I'm just going to add up these 5 numbers, and that will be our answer. So we got our 4020 plus 452,000 plus 83720 plus 66600 plus 14100, and you get that. So 620,000 and what was it? 440. So that is how much energy it takes to take a 0.2 kilogram chunk of ice from negative 10 degrees Celsius all the way up to 110 degrees Celsius by following the heating curve. And if we were going the other way, if we were going backwards, if we were cooling the water off, then we would get the same answer. It would just be negative. Okay? So that is how you use water's heating curve, latent heat, to figure out those sorts of problems.